All right, this is going to be the solutions for Unit 5, Worksheet 6. And we'll start with number 1. I'm just going to read off the problems and then we'll work them out kind of together. So number 1 has a sled weighing 300 newtons pulled at a constant speed or over a horizontal floor by a force of 50 newtons applied parallel to the floor. So remember, the first thing we're going to do is we're going to write down our knowns. And so we know right off the bat FG, and I'm going to click down here, size or 2. FG is equal to 300 newtons. Okay. We're at a constant speed, so constant speed means acceleration is equal to 0. And if acceleration is equal to 0, I'll also know that the sum of forces is always going to be equal to 0, because remember that unequal forces, so if the sum of forces is not equal to 0, then there's going to be some kind of acceleration. So I know acceleration is equal to 0, so I know the sum of the forces in every direction is going to be equal to 0. This sled is going to be pulled at a constant speed, so we're going to call that FT. And FT is going to be 50 newtons. Okay, so the first thing we're going to do is do a force diagram. So A is to draw a force diagram for the sled, and we'll make this as quantitative as we can as we're going along. So force diagram. So we got the sled. We're going to have FG. Let me get my palm on here a little bit. FG, and our on by here is sled earth, and we know that that is 300 newtons. Okay, going up is a normal force. On by here is sled and ground, and I know that this sled is not accelerating up or down. Forgot my minus here as usual. So I know that the normal force is going to be plus 300 newtons to balance out the up and the down. The other thing I know is that I've got a pull force, so we're going to call that FT, and that is going to be equal to 50 newtons. And because this is moving at a constant speed, I also know that there's friction force, and that's going to be sled surface. And that will be equal and opposite, so minus 50 newtons. I forgot my on by over here. So sled and let's say rope. So there's A. And then it says B, find the coefficient of kinetic friction. And so B, I want to find, so friction is mu. It's like a U with a straight line on the front edge. And we have both static and kinetic, and to tell those apart, we'll just put a K in front of them. We find them the same way, no matter what we do. Okay, so our original formula that we start out with says that our force of friction is going to be mu times the normal force. And this is the normal force pushing out perpendicular to the surface as a result of, in this case, as a result of gravity. So it'll be the one going up. And so I want to find this. So what I'm going to do is I'm going to kind of rework that formula, and it's going to be the force of friction divided by the normal force. Okay, and so that's fairly straightforward. Force of friction is minus 50 newtons, and the normal force is 300 newtons. And so I will end up with a normal force of about 0.17. And that's where we're at. Now, the reason I don't have a negative here is the coefficient of friction is just a comparison value. It doesn't have units, and it doesn't have signs. Okay, so it wouldn't matter if it was plus or minus, but there are no units because normal or newtons and newtons cancel out. So then the last thing we need to do, let me make a little room here, is that we want to find the sled's acceleration if the coefficient of kinetic friction kinetic friction was 0. And so if UK, oops, a little sloppy with that, equals 0, what is A? Okay, so in this case, if UK equals 0, the normal force is going to stay. Normal force is a result of the floor pushing up, or the ice pushing up, or the snow pushing up. So the normal force doesn't change. But if UK equals 0, force of friction is equal to U sub K times normal force. And so that's going to be equal to 0 because U sub K is equal to 0. If I look at my original drawing, I had a force of friction of minus 50 and a tension force of plus 50. Now, in this scenario, my friction force is minus 50, or it's not minus 50 anymore, it's 0. And so I have an unbalanced force. I have a sum of forces in the x direction that's equal to the tension force, which is 50 newtons, plus the friction force, which is 0 newtons. And that's also equal to mass times acceleration. Okay, so I'm almost there. So the unbalanced force, the sum of forces in x direction, 50 newtons, is equal to ma. And if I rework that a little bit, 50 newtons over m would equal a. My one little problem, I don't have m. But if I go back to my original up here, I had a 300 Newton force of gravity, and from that I can figure out mass. So force of gravity equals mass times acceleration. So if I work that over, and if it's gravity, A becomes force of the acceleration due to gravity, which is g. So minus 300 newtons over minus 9.8 newtons per kilogram, which is the same as meters per second squared. And that's going to give me a mass of 30.6 kilograms. If I take time to calculate that out, and I'm cheating because I have a written copy right next to me. Okay, so let me rework this again. So 50 newtons, 50 newtons over 30.6 kilograms is going to equal A, and that's going to equal 1.6 meters per second squared. That's the same as newtons per kilogram. So that's number 1. All right, for problem number 2, this is an odd problem. It's counterintuitive from what we've been doing because we've got a block being pushed against a wall. Imagine holding a book against the wall and keeping it from sliding down would be friction plus the force that you're applying to the wall. So in this one, the normal force isn't going to go in a way that you're used to, where you're kind of used to that the normal force is from the ground pushing up on an object. And here, we're applying force to the wall, and there's going to be a normal force pushing back. So when I push on the wall with the book, so the wall pushes on the book as the book pushes on the wall. So we're going to set up kind of sideways here. So it says a 50 Newton force is applied to a 0.5 kilogram book. Friction keeps the book from sliding down the wall. And so part A is going to be to make a force diagram. So let's go ahead and put down what we know. So we know that the weight of the book is force due to gravity, and that's going to be 15 newtons. And that's going to go in a downward direction, so we'll put that as a minus 15. And we know, whoops, that's not, I'm doing that wrong. So it's not force due to gravity, it's me making a mistake. So let's, we'll go back and we'll erase that a little bit. And we'll call that a push force because, I don't like to make mistakes. So this is going to be a push, so we'll call that a normal force. That's a push. So we're going to push on the wall, and then I got to take that minus off of there because that's going to be in the right direction. There we go. All right. Mass of the book is going to be 0.5 kilograms, and that's where I realized I'd made a mistake because force due to gravity is going to be based on that mass. All right, and we know we have some book keeping it from sliding down the wall, so we know the book stays in place, and we know that acceleration is going to be equal to 0, and so net force can be equal to 0. So all these things are going to balance out. All right, so if we make a force diagram, here's our book. We're going to have gravity force, and that's going to equal mass times acceleration, so 0.5 kilograms times minus 9.8 newtons per kilogram. And in my head, if I'm doing that right, that works out to 4.9 newtons minus 4.9 newtons. And because the book isn't sliding, there is some force going up. We can't label that one yet, but that's equal to this, and that's going to be plus 4.9 newtons. It is not normal force. And then we've got this push force. I'm going to call it FNP because all the pushes are normal, but we'll say this is FN from the push. And as was given, so the on by here is book by, well, we'll say hand. And so this one, the on by was, I'm just going to put initials, book, earth. And this push force is 15 newtons. And here is where our normal force is. And this is on the book by the wall. So the book is pushing on the wall's pushing back. And that's going to be minus 15 newtons, equal and opposite. If it wasn't equal and opposite, the book would be either accelerating toward or away from the wall. So now we've got a force diagram, and it's quantitative. It's got numbers for all of them. For part B, we want the coefficient of static friction. So that's mu s. And we want to know the coefficient of static friction that will keep the book from sliding. And so that we can find as a proportion of the friction force divided by the normal force. And this normal force is going to be from here. Okay. And so the friction force we already had, that was 4.9 newtons. And tension force was 15 newtons. Again, the signs don't matter here. It's actually, if I did it right, it would come out to a negative number. But this is about a third. So roughly 0.33. 5 over 15 would be 0.33333. It's a little bit less than that. So, but there's where we are for mu sub s, coefficient of static friction. No units, no signs. Okay, for number 3, we have a horizontal 100 Newton force applied to a 50 kilogram classmate resting on a level tile floor. The coefficient of kinetic friction is 0.15. Okay, so our first step is to draw a force diagram to represent this situation. And so we can start out doing that. Let's say this is A. And so we're going to have our student. Okay, we have FG. And this is going to be, so person, Earth. Equals MA. And so from that, we can figure out that the person is 50 kilograms times minus 9.8 newtons per kilogram. And that will come out to minus 490 newtons. Okay. Classmate is not floating up into the air or sinking into the surface. This one has a normal force going right where we'd expect. My pen will work like I expect, so this is Fn, okay, and this is going to be person, floor, equal and opposite to the gravity force, and that is going to equal 490 newtons. Okay, they are being pushed with 100 Newton force. Oops, I accidentally erased my little dot there. Okay. And so we're going to call this an FN. This is also a normal force because it's a push, but this is not the special one. This is person. And we're going to say the push. Because I don't know what the push is. And that's equal to 100 newtons. Okay. And we have to figure out the friction force. Okay. There's going to be a friction force. We just have to figure it out. And the on by here is going to be person, floor. Okay. So to figure this out, force of friction is going to be mu, and this is moving, so it's mu sub k, the coefficient of kinetic friction, times the normal force coming up from the floor. Okay, and so our coefficient is 0.15 times 490 newtons. And so we're going to have to just be conscious of the fact that our direction for that friction force is going to be to the left, so it's going to have to be negative when we're done. And 0.15 times 490 is 73.5 newtons. And it's got to be negative. Okay, so there we've got the force diagram done. It is unbalanced, so this arrow to the left, force of friction, is smaller than the arrow to the right, so we're going to accelerate in this direction. Which takes us to step B, which is what is the acceleration of the student. So B, we're going to be looking for the sum of forces in the x direction, because that's where they're unbalanced. And that's going to be equal to Fn plus Ff. And if I do that, I'm going to end up with 100 newtons plus minus 73.5 newtons. And it's a little bigger in the positive direction, to the tune of 26.5 newtons. And so from that, we can figure out acceleration. So remember that this quantity here is equal to ma. So this is equal to ma. So A is equal to 26.5 newtons divided by the mass. And so we have to go back and look, and we had a mass of 50 kilograms. And so we have 26.5 newtons over 50 kilograms, and that works out to 0.53 newtons per kilogram, which is also equal to meters per second squared. So that's the acceleration. All right, I'm going to slide up, make a little more room here. And we're going to go back and we're going to put in C. And in C, we said, suppose the classmate was sitting on a carpet where the coefficient was static friction was 0.25. Is the horizontal 100 Newton force sufficient to cause the classmate to accelerate? So we have to figure that out. We have to draw a force diagram again, and then explain why or why not. All right, so force diagram. We can kind of reuse some of the stuff we had from up above. And I'm not going to do the on-bys this time because I'm just that lazy. Okay, and so from before we had FG was minus 490. If you're not sure what the on-bys are, you can go back up and look up above. Normal force on the person by the floor is going to be positive 490. And our push force to the right is going to be, and that's a normal force also, but that's also going to be 100 newtons, just like before. And now we have to calculate a new force of friction. So a new force of friction is going to be the new kinetic coefficient of friction times Fn. And so that is going to be 0.25 times 490 newtons. And that is going to equal 122.5 newtons. Okay, so the force of kinetic friction that we'd have to overcome to move this is 122.5 newtons. So here's the weird part. We can't have more kinetic friction than we have push, meaning, in other words, that the friction can't be bigger than the normal force. So the friction force is going to be 100 minus 100. So basically it's going to sit still. But in order to break free, in order to get this person to move, we would have to have an Fn. So in order to move, the person, the Fn, the push, okay, would have to be greater than 122.5 newtons, and it's not. So we put the three little dots. I mean, therefore, it won't move. Okay, so this is kind of a counterintuitive thing again. So it says that the force of friction using the kinetic coefficient of friction here would be 122.5 or minus 122.5 newtons. But the friction force can't be any higher actually than the force that's being applied to the person. So it can't be bigger than 100 newtons if it's only being pushed with 100 newtons. But that 100 newtons is not enough to make it move. So the answer is no, it won't move.